Welcome to the deep dive. Today, we're really getting into something that, well, powers basically everything we do. The uses of electricity.
It really is fundamental, isn't it?
Absolutely. And we've got some great source materials here, study guides, FAQs, briefing notes, kind of like a consolidated guide.
Yeah, a good mix to pull from.
Our mission today is simple. Unpack how we use this amazing force, look at the core ideas, the different applications, make it all clear, and hopefully pretty engaging for everyone listening.
Sounds good. It's fascinating stuff, the sheer breadth of it all. You look at these materials, and it's not just lights on, lights off.
No, exactly. It underpins so much. So, here's the plan for this deep dive. We'll start with the basics, the concepts or sources layout.
Like electroplating, electromagnetism.
Right. Electroplating sounds niche, but it's got cool uses. Then, yeah, electromagnetism, which feels a bit like magic sometimes.
Huh. It can seem that way.
Then we'll look at harnessing the sunlight, solar power, obviously, how we use electricity for heating things up.
Resistive heating, induction heating.
Yep. And all the ways we make light. Incandescent, fluorescent, LED, the whole spectrum.
Covering all major types.
And then to kind of lock it all in, we'll run through some practice questions from the end of the chapter materials. How's that sound?
Perfect. Build the foundation, then see how it applies. Let's do it.
All right. Let's kick off with electrochemistry, specifically electroplating.
Okay.
Now, you might hear electroplating and think, heavy industry, but it's actually pretty common.
Definitely. Think about jewelry, for instance. That gold or silver layer, often electroplated.
Exactly. So the sources tell us it's basically using electricity to move tiny charged metal particles.
Ions, right?
Positive metal ions, yeah. They're dissolved in a liquid, a solution.
And they get transferred onto a metal object that has a negative charge.
Right, opposites attract. The positive ions in the solution move towards that negatively charged object we want to coat.
So it's an electrical delivery system for metal atoms, essentially.
That's a good way to picture it. And it's not just for looks, though that's a big part, like with jewelry. Right, aesthetics, making things shiny or giving them that gold finish.
But also protection, giving a base metal a coating that resists rust or wear. Think electronics sometimes, too.
Good point. And the basic setup, according to the materials? Pretty logical. You need a few key parts.
Yep. You need your source metal, the anode.
That provides the ions.
Right. And the object you're plating, that's the cathode, which is negative.
Okay, anode positive, cathode negative. Got it.
Then you need the liquid, the electrolyte solution, for the ions to travel through.
Kind of like the highway for the ions.
Exactly. And, crucially, a DC power source to provide the electrical push and pull.
Direct current. Okay, makes sense. So electricity creating thin metal layers. Cool. Let's switch gears to electromagnetism.
Ah, yes. A huge one.
This is where electric current, the flow of electrons in a wire, actually creates a magnetic field around the wire.
That's the core principle. It's this incredible link between electricity and magnetism.
And this link, this effect, it powers so much, doesn't it? Our sources list quite a few applications.
Oh, absolutely. Motors, for starters, converting electrical energy into motion. Think fans, pumps, electric cars.
Everything that spins, basically.
Pretty much. Then you flip it around and you get generators, mechanical motion turned into electricity. That's how most power plants work.
So motors use electricity, generators make it, both using electromagnetism.
Exactly. Then you have relays. Those are basically switches that are flipped using an electromagnet.
An electrically operated switch. Okay.
And transformers, absolutely essential for the power grid. They change AC voltage levels up or down.
Right, to send power over long distances efficiently and then step it down for our homes.
Precisely. And the materials mention a figure 5.2, which sort of visualizes how this magnetic push and pull works in motors and generators. It all comes down to that interaction between the current and the magnetic field.
Amazing that one principle drives motors, generators, relays, and transformers. Okay, next up. Harnessing light, photoelectricity, and solar PV.
Sunshine power.
Yeah. So photoelectricity, this happens when light particles, photons,
Tiny packets of light energy.
hit certain materials, semiconductors, and knock electrons loose, making them flow. That flow is an electric current.
Correct. It's a direct conversion of light energy into electrical energy. Figure 5.3 in the materials shows a cross-section of a solar cell, illustrating those layers where this happens.
So the light comes in, hits the special material, zap, electricity starts flowing.
That's the essence of it. And this effect is what powers solar photovoltaic systems, PV systems.
And a PV system isn't just the panel itself, right? It's the whole shebang.
Right. It's the panels, the inverter to change the DC electricity to AC for our homes, the wiring, mounting, everything needed to capture solar energy and turn it into usable power.
Primarily for powering buildings, that's the main use we see.
That's a huge application, yes.
Yeah.
But the sources list a lot more.
Yeah, I saw that. It's not just rooftops, like billboard lighting.
Yep. Especially useful for billboards in locations far from the grid. Solar makes them self-sufficient.
And those interstate call boxes. Often solar-powered, too.
Makes sense. Need them to work reliably, even if the main power's out. Solar plus a battery does the trick.
And out on the water, navigational markers, boobies. The materials show one in figure 5-5. They use PV to charge batteries for their lights.
Exactly. Critical for safety, guiding ships at night. Again, ideal for remote, off-grid applications.
Then roadside signs, highway signs, direction signs, safety warnings.
Figure 5.4 shows some examples. More and more are using solar panels now. Less wiring needed.
And those flashing warning signs near schools, traffic signal warnings, also often solar. Figure 5-6 highlights that.
Very common application now. Localized power, enhanced safety.
The list keeps going. Remote telecoms equipment, weather stations way out somewhere.
Mountaintops, deserts. Anywhere hard to reach with power lines, solar PV is often the answer.
And finally, photocells, those little light sensors. Figure 5-7 shows one.
Right, also called light-dependent resistors. They sense how much light there is.
And they can trigger switches, right, like turning street lights on when it gets dark.
Precisely. They automate lighting based on ambient light levels. Uses that same photoelectric principle.
Okay, so solar's doing way more than we might initially think. Now, let's talk about making heat with electricity. Two main ways mentioned: induction and resistance. Let's start with induction. Sounds fancy.
It kind of is. It's clever. With induction heating, you pass alternating current through a metal object, but specifically a ferrous metal one containing iron.
Okay, AC current, iron-containing metal. What happens?
That AC current creates a magnetic field that's constantly switching direction, expanding and collapsing. This changing field induces electric currents right inside the metal object itself.
Ah, so the electricity isn't flowing through the object from outside to heat it directly.
Not primarily. It's the magnetic field causing currents within the object, and those internal currents generate the heat due to the metal's resistance.
Okay, interesting. And the sources mentioned something called hysteresis. Figure 5-8 illustrates this.
Right. Hysteresis is another heating effect happening at the same time in ferrous metals. Think of the tiny magnetic bits inside the iron. The molecules.
Okay.
The rapidly alternating magnetic field forces these molecular magnets to flip back and forth constantly. This internal friction, this resistance to flitting, generates heat.
Wow, so it's both induced currents and this molecular flipping causing the heat.
Exactly. Both contribute in induction heating of ferrous materials.
Where do we see this?
Some modern stovetops use it. They heat the pot or pan directly, very efficiently, while the cooktop stays relatively cool.
Ah, the induction cooktops. Got it.
And it's used in industrial processes, too, for very fast, controlled heating. Figure 5.9 gives some industrial context.
Okay, now the other method, resistance heating. This sounds more straightforward.
It is. It's the most common type.
Yeah.
The principle, shown in Figure 5.10, is simple. You pass electric current through something that resists the flow, a heating element.
The wires in a toaster.
Exactly. As the electrons push through that resisting material, their energy gets converted into heat. It's like electrical friction.
Makes sense. And the applications are, well, everywhere, right?
Pretty much anywhere you need electric heat. Toasters, ovens, ranges, water heaters, clothes dryers, space heaters, clothes irons, all use resistance heating elements.
Super common. Now, the materials also bring up thermocouples here, but they're more for measuring temperature or safety.
That's right. A thermocouple itself, like in Figure 5.11, is made of two different metals joined at 2 points. If those two junctions are at different temperatures, a small voltage is produced.
So temperature difference creates electricity.
A tiny amount, yes. And the voltage is proportional to the temperature difference, so you can use it to measure temperature accurately.
Okay. How does that relate to safety, like in a gas furnace?
Ah, the classic safety application, shown in Figure 5.12. Many gas appliances with a pilot light use one. The thermocouple tip sits right in the pilot flame.
So it gets hot from the pilot.
Right. And that heat generates that small voltage we talked about. This voltage is used to power a small electromagnet that holds a safety gas valve open.
I see. So the electricity generated by the pilot light's heat keeps the gas valve open. Ingenious.
It really is. Because if the pilot light goes out...
The thermocouple cools down.
Exactly.
Okay.
It cools, the voltage drops. The electromagnet isn't strong enough to hold the valve open anymore.
And the valve closes, shutting off the gas.
Correct. Prevents unburnt gas from filling the space. A crucial safety feature, all based on that simple thermoelectric effect.
That's really clever. Okay, let's move to our final big topic, electric lighting.
Let there be light.
Indeed. The sources say light is produced mainly through incandescence, electric discharge, or LEDs, and Figure 513 gives a nice overview.
And they make a point about efficiency, especially with the old incandescent bulbs.
Yeah, that was eye-opening. Less than 5% of the energy actually made light.
Yep.
The rest, like 95%, just heat.
Incredible waste, really.
Yeah.
Which is why we've moved towards better technologies.
Let's break them down. First, incandescent. The classic bulb. How does it work? Figure 514 shows one.
Simple principle. Run electricity through a thin wire, a filament, usually tungsten.
Inside a glass bulb.
Right, often in a vacuum or inert gas. The filament has resistance, so it gets incredibly hot from the current.
And when it gets hot enough, it glows.
It glows white hot, emitting visible light. That's incandescence. Hot enough to shine.
Simple but inefficient. Okay, next category. Electric discharge lighting. Sounds like sparks are involved.
Sort of. The general idea, shown across figures 515 to 517, is you create a high-voltage arc and electrical spark between two electrodes.
Inside a tube filled with gas.
Exactly. A tube with gas like argon or xenon at low pressure. The arc excites the gas atoms, causing them to release light.
And fluorescent lights fit in here. Still see those everywhere.
Yeah.
Figure 515.
Yes. A fluorescent tube has argon-xenon gas plus a tiny bit of mercury vapor. The electric arc excites the mercury, making it emit ultraviolet UV light.
But UV isn't visible.
Correct. So the inside of the tube is coated with a white powder, a phosphor. The UV light hits the phosphor.
And the phosphor glows with visible light.
Precisely. The phosphor converts the invisible UV into the visible light we see.
A two-step light conversion. Clever. What about neon lights? Figure 516, all those bright signs.
Well, true neon gas gives off that reddish-orange color.
Ah, okay.
To get other colors, they use different gases, argon, helium, krypton, or different phosphor coatings inside the tubes, sometimes combined with mercury, like fluorescence. The electric arc excites whichever gas or phosphor is in there, producing specific colors.
So neon sign is kind of the general term, but the actual color depends on the gas or coating inside.
You got it. Used mostly for signs and decoration.
And then, still under electric discharge, we have HID, high-intensity discharge, figure 517, 518, stadium lights, right?
That's a prime example. These produce very bright light. The arc happens in a small tube containing argon, xenon, and metal vapors, like mercury or sodium or metal halides.
Metal vapors.
Yeah, the heat from the arc vaporizes small amounts of metal salts inside the tube. Exciting these metal vapors produces incredibly intense light, perfect for lighting huge areas.
Makes sense for sports fields or big parking lots. Okay, final lighting type. LEDs. Light-emitting diodes. Figure 519.
The current champion, really. LEDs work differently. They use a semiconductor device.
Not heating a filament, not sparking through gas.
Nope. Direct current passes through the semiconductor material. Inside, electrons combine with holes places lacking electron, and this combination releases energy directly as photons, as light.
A solid-state way of making light, and the advantages are huge, according to the sources.
Oh yeah, much longer lifespan than other types.
Here they last ages.
They turn on instantly, no warm-up. They produce way less heat, which means less wasted energy and lower cooling costs in buildings.
Or efficient.
Much more efficient, more light output, lumens for each watt of electricity used. Plus, you can get them in almost any color directly, without filters.
So, longer life, instant on, less heat, wide color range, super efficient. It's easy to see why they're taking over.
Absolutely. They're positioned to replace pretty much all other lighting types eventually.
Okay, wow. We've covered a ton of ground electroplating, magnets, solar, heat, all kinds of light. Feels like we've hit all the main uses from our sources.
It's a pretty comprehensive overview of how electricity shapes our technology.
Definitely. Now, to make sure this all sinks in, let's tackle those practice questions from Chapter 2. We've got the answers circled here. Let's just quickly confirm them and why they're right. Ready?
Let's do it. Good way to recap.
Question 1. ADAS has many uses. The most common include electrochemical processes, electromagnetism, solar PV systems, heat, and lighting. Circled answer is A, electricity. Seems obvious, right? That's the core subject.
Yep. Electricity enables all of the others listed. Straightforward.
Question 2. ACE uses electricity to transfer dissolved, positively charged metal to the surface of a negatively charged metal. Answer. A, electroplating. That's exactly the definition we started with.
Correct. The key process for coating metals using current.
Question 3. From current flow is used for many applications such as motors, generators, relays, and transformers. Answer B. Electromagnetism. The magnetic effect of current is the basis for all those devices.
Spot on. The interaction between electricity and magnetism is fundamental there.
Question 4 is the conversion of light energy into electrical energy. Answer is A, photoelectricity. That's the direct conversion effect used in solar cells.
Correct. Light in, electricity out.
Question 5. A solar system combines all components and subsystems that convert solar energy into electrical energy. Answer B, photovoltaic, PV. It specifies the type of solar system.
Right. Photovoltaic is the technology doing the direct conversion.
Question 6. Heating occurs when an expanding and collapsing electromagnetic field from current flow passes through ferrous metal, iron. Answer B, induction. That magnetic field effect inducing heat.
Precisely. Characteristic of induction heating.
Question 7. When the electromagnetic field changes polarity, the ferromagnetic molecules reverse their electromagnetic polarity. This is known as answer, hysteresis. That internal molecular friction heating.
Correct. Hysteresis loss manifesting as heat in ferrous metals under AC fields.
Question 8. The principle of heating is that when current flows through a heating element, the movement of the electrons against the resistance converts electrical energy into heat. Answer C, resistive. Simple electrical friction.
Exactly. The most basic form of electric heating. Toasters, ovens, etc.
Question 9. A typical application of thermoelectricity is a temperature measuring device that produces a voltage when junctions. Answer C, thermocouple, the device that uses the thermoelectric effect.
Correct. Thermocouple is the sensor.
Question 10. If the pilot light goes out, the thermocouple cools down, reducing the energy output to the point that the shutoff valve, answer C, closes. The safety function we discussed.
Crucial safety mechanism. Cooling thermocouple shuts the gas valve.
Question 11. An electric light is a device that produces through the principles of incandescence, electric discharge, or a light-emitting diode LED. Answer B, illumination. The purpose of a light.
Right. Illumination just means light production.
Question 12. Light is produced by heating the filament within a light bulb to a high temperature. Answer B, incandescent, heating until it glows.
The defining feature of incandescent bulbs.
Question 13. Lighting such as fluorescent, neon, or high-intensity discharge produce light from a high-voltage arc between electrodes in a gas tube. Answer A, electric discharge. The umbrella term for lighting that uses an arc through gas.
Correct. That category covers fluorescent, neon, and HID.
Question 14. When a high-voltage arc in a bulb, ultraviolet radiation is emitted causing the phosphor coating to glow. Answer B, fluorescent. That UV to visible conversion via phosphor is specific to fluorescence.
Exactly. The phosphor is key.
Question 15. Light is produced when an electric arc travels through a glass tube filled with a mixture of gases and phosphors. Answer B, neon, referring generally to those colorful sign tubes.
Right. Using different gas phosphors for color.
Question 16. Light is produced in high-intensity discharge lighting when an electric arc travels through a glass tube filled with argon, xenon, and gaseous metal vapors. Answer B, HID. The metal vapors are the giveaway for high-intensity discharge.
Correct. That's what makes them so bright.
And last one, question 17. When direct current passes through a semiconductor device known as a PHY, light is produced. Answer B, light-emitting diode, or LED.
Yep. The semiconductor emitting light. That's an LED.
Excellent. Went through all of them. Hopefully that helps solidify things for everyone listening. It feels like we've really covered the landscape of electricity's uses.
I think so too. Connecting the principles to the applications and then reinforcing of the questions provides a solid picture.
So wrapping up this deep dive, we've seen electricity doing amazing things, from, pleating metal atom by atom to creating powerful magnetic fields, capturing sunlight, generating heat in different ways, and lighting up our world through various technologies.
It truly is versatile. Understanding these core principles really helps decode so much of the technology around us.
It does. It gives you that framework. So here's a final thought to leave everyone with, something to chew on.
Okay.
Given everything we're hearing about energy efficiency, sustainability, renewable resources, how do you think these uses of electricity we talked about today might change?
That's the big question, isn't it?
Right? How might lighting evolve further? Or heating? Or even things like motors, driven by that need for efficiency and sustainability? What new ideas might spring from these basic principles as we look ahead?
It's almost certain that innovation will continue, driven by exactly those pressures. We'll likely see even more efficient ways to generate light, perhaps smarter heating systems, maybe breakthroughs in energy storage linked to solar.
Hmm.
The principles might stay the same, but the applications could look quite different.
A lot to think about.
Right.
Well, thanks so much for joining us on this really illuminating deep dive into how we use electricity.
My pleasure. Always
Mm.
fascinating to revisit these fundamentals.
Until next time, keep thinking about how the world works.